Welcome to another episode discussing the research projects developed by the Applied Computing Research Group, GCA. Imagine you are running a massive factory, but all the lights are completely turned off.
Okay, a pitch black factory.
Right, and you can hear all this heavy machinery running in the dark. You can hear boxes falling off the conveyor belts just crashing onto the floor, and you're bleeding millions of dollars a day, but you can't see why.
Wow.
Yeah. Welcome to the reality of modern enterprise cloud computing.
That is, honestly, it's a phenomenal way to visualize the problem. I mean, when a physical engine is inefficient, you can see the smoke, right? You measure the extra gallons of gas it burns.
Right, the bottleneck is tangible.
Exactly. But you step into the hidden software engines running in the cloud, and you just lose that visibility completely.
Mm-hmm.
We're operating in this digital landscape where inefficiencies are basically invisible, yet they are incredibly, incredibly expensive.
Which brings us to our mission today. We are turning the lights on in that factory. So we are doing a deep dive into a comprehensive survey on the performance of enterprise application integration platforms, or EAI platforms.
Yeah, EAI.
And we really need to highlight the authors here, because this research was developed by Daniela L. Frere, Raphael Z. France, Fabricia Roos France, and Sandra Sawicki. And they're all from the Department of Exact Sciences and Engineering at Unigir University.
And, the stakes they outline in this paper are just massive. I mean, whether you are managing a corporate IT budget or your engineering software, or honestly, even if you're just a curious user wondering how your various cloud apps communicate so seamlessly, you're interacting with these hidden software engines.
Right, the things running behind the scenes.
Yeah, they're called runtime systems. And the efficiency of these systems, it dictates not just the speed of your applications, but staggering financial costs at the enterprise level.
So before we get into the platforms themselves and this whole report card the researchers put together, we really need to understand what an enterprise application integration platform is actually doing.
Right, let's break it down.
Because we know companies use dozens, sometimes hundreds of different applications, right? You've got an HR system from one vendor, a payroll system from another, a customer database from a third, and literally none of them were designed to speak the same language.
Yeah, they're all in their own little bubbles. So an integration platform is essentially this universal translator. It's an orchestrator. It sits right in the middle of all these isolated silos. And to pull this off, the platforms use what is known as a pipes and filters architectural style.
Okay, pipes and filters. Let's make this concrete with that digital assembly line idea we talked about.
Yeah, let's do it.
So the pipes are the conveyor belts, right? Moving the data from one end of the factory to the other. They are the message channels. And the filters, those are the robotic arms stationed along those conveyor belts doing very specific atomic tasks. So one robotic arm might grab an incoming data package and translate a currency from euros to dollars.
Yep.
And then another arm down the line might take a new hire's HR profile and automatically sync the relevant details over to the payroll system.
That's a great analogy.
Right.
And the runtime system of the platform, that is the underlying engine generating the electricity for that entire factory. I mean, it provides the core computational resources specifically. It provides what we call threads of execution to make sure those robotic arms actually have the power to move.
But wait, I have to push back on this a little bit.
Sure.
Hardware gets faster and cheaper every single year. We have these massive cloud server farms that span entire city blocks. So why are researchers so hyper-focused on the software efficiency of these runtime systems?
It's a valid question.
I mean, if the software is a little bloated or slow, the old industry mindset was just, throw more hardware at the problem. Just add another server, right?
Right. And that mindset totally made sense a decade ago when your company's servers were sitting in a freezing cold closet down the hall. You already bought the server.
Right.
But this research points to a pivotal shift in the industry around 2016, moving toward IP as integration platform as a service.
Ah, okay. The shift to the cloud.
Exactly. If we connect this to the bigger picture, the traditional on-premise market for these platforms was growing by less than 10%. But the IPaaS market, the cloud-based version, it exploded by 60% in a single year.
Wow, 60%. That's representing hundreds of millions of dollars migrating to the cloud.
Yeah, and because the cloud uses a pay-as-you-go charging model, the math just changes completely. In the old days, if your software was inefficient, it just made a server you already owned run a little hot. You had already sunk the capital into buying the metal, so it didn't really matter.
You pay for it already, yeah.
Today, the cloud converts those capital expenses into operational expenses. So inefficient software directly drains your bank account in real time.
Because you're paying for the electricity, basically.
You're paying for every single ounce of computational power. Every core utilized, every megabyte of memory consumed per second, every millisecond a thread is active. It is all metered.
Oh, wow. So efficiency literally equals money.
Exactly.
If your digital assembly line is sluggish, or if those robotic arms are wasting electricity just waiting for a box to arrive, your monthly cloud bill just skyrockets.
That does.
Which really leads to the core problem the researchers tackled here. If a slow runtime system is basically a leaky pipe draining money, how do you actually measure the leak? I mean, you can't just use a stopwatch.
No, you can't. They had to build a custom evaluation framework from scratch. So they grouped 10 different properties into two main dimensions to, capture the full picture of performance.
Okay, let's unpack this, because the first dimension they talk about is message processing, right?
Yep, message processing.
This is the brute force metric. It is all about raw efficiency and just increasing the sheer volume of messages processed per unit of time.
Yeah, it's the muscle.
Right, the muscle. The researchers looked at properties like whether the system utilizes multi-core processors, how it stores messages, if it can distribute execution across multiple virtual machines, and the configuration of its thread pools. It's basically the horsepower of a delivery truck. How fast can you push data from point A to point B?
Horsepower looks great on a spec sheet, right?
Mm-hmm.
But it isn't everything. And that brings us to the second dimension, which is fairness execution.
Fairness execution. That sounds a bit more nuanced.
Highly nuanced. Fairness looks at how the computational resources, the threads themselves, are assigned to tasks to minimize wait times. They evaluated things like starvation detection, thread pool policies, execution models, and whether the system understands task complexity.
So fairness execution is essentially your air traffic control.
That's a perfect way to put it.
I was looking at the breakdown in the paper, and what blew my mind is that a system can have incredible throughput, like amazing message processing, but absolutely terrible fairness execution.
Yeah, and what's fascinating here is that discrepancy. Imagine you have 100 tasks hitting the platform at once.
Right.
99 of them are tiny, simple operations like a 2-kilobyte password reset email.
Super fast.
Right. But one task is a massive, complex 50-gigabyte quarterly database migration.
Oh, man.
Yeah. So a system with poor fairness might process those 99 simple tasks instantly, making its overall speed look fantastic on paper.
Right. The average speed looks great.
Exactly. Meanwhile, that massive task blocks the queue. Or, conversely, the massive task hogs all the resources, and a crucial tiny password reset waits in line for 10 minutes.
Which is an eternity in computer time. And the researchers call that starvation, right?
Yes, starvation.
And if you think about the audience dealing with this, like the IT professionals and developers, starvation is the nightmare scenario. It's getting a frantic phone call at 3 a.m. from an executive because a critical alert email didn't go through, all because the system was blindly prioritizing some mundane background update.
Exactly. To have reliable performance in an enterprise environment, you need both raw speed and intelligent traffic control.
Okay, so taking that two-dimensional framework, the horsepower and the air traffic control, the researchers basically handed out a state-of-the-art report card.
They did.
They evaluated 9 prominent open-source integration platforms. Let me list them. We've got Camel, Guarana, Fuse, Jitterbit, Mule, Pedals, Service Mix, Spring Integration, and WSO2.
That's the list, yeah.
So let's talk about where the industry is actually doing well. Because I noticed in the data that almost all these platforms have figured out distributed process execution.
Right, they have.
They can spread the workload across multiple virtual machines to scale up when the load gets heavy. But there was one glaring exception, wasn't there? Guarana.
Yeah, Guarana stands out there, mostly due to its architectural limitations at the time of the study. It was operating more like a monolith, tied to a single machine's resources.
Which is bad for the cloud.
Very bad. It severely limits its ability to scale horizontally across a massive cloud environment. But the rest of the pack performed really well on distribution. They also generally agreed on the best approach to message storage, utilizing what is called hybrid message storage.
Right, and that makes total sense, because if you keep every single message and data packet in the active memory, the RAM, it's incredibly fast.
Lightning fast.
But the moment a massive file comes through that exceeds the RAM, it overflows and just crashes the entire system. So hybrid storage smartly moves those large data streams from the fast memory down to the hard disk so the system doesn't buckle.
Yeah, finding that balance between speed and stability is exactly what led the researchers to identify the overall winner of this evaluation.
Ah, the winner.
The platform that checked the most boxes, particularly in how it defends itself against system failure, was Mule.
Mule.
Yeah.
Yeah, Mule really separated itself from the pack in a few clever ways. First, it allows software engineers to do fine-grained configuration of their thread profiles, so you aren't stuck with a one-size-fits-all setting.
Right, customization is key.
You can dedicate one specific profile just for receiving messages, ensuring you literally never miss incoming data, and then build a totally different profile for dispatching them.
And Mule also tackles that hybrid storage issue with extreme precision. Instead of just blindly jumping data to the disk when memory gets full, it sets an initial, highly controlled memory buffer of exactly 512 kilobytes.
Just 512 kilobytes, that's really specific.
Very specific. If the data stream gets larger than that, it automatically creates a temporary file on the disk to prevent overflow, and then it expands that buffer in 512 kilobyte increments. It's a highly predictable, mathematically sound way to handle spikes.
I also read it uses a virtual runtime cluster for high availability, which basically ensures that if one node goes down, the whole system doesn't collapse. And perhaps most importantly, Mule has excellent throttling capabilities.
Throttling is so important.
It really is. Throttling is basically a bouncer at the door of an exclusive club. If the club is full, the bouncer stops letting people in. Throttling controls the rate of incoming messages, so the internal components aren't just crushed by a sudden, denial of service level spike in traffic.
So what stands out to you when you hear all that? When you step back and look at Mule's winning features, the fine-grained profiles, the precise 512 kilobyte buffers, the clusters, the throttling, they all share a unified philosophy.
You're defensive.
Exactly. They're all defensive mechanisms. Mule won because it is the best at protecting the system from drowning in sudden, unpredictable waves of data.
Okay, and here's where it gets really interesting. If protecting the system from drowning is the best the industry can do, that raises a much, much larger issue. Because here is where the research gets deeply concerning.
Oh, yeah.
While Mule performed the best, the real story of this research isn't what these 9 platforms can do. It's the shocking list of basic technological advancements that literally none of them are utilizing.
It is a massive revelation. We are talking about the quote-unquote state-of-the-art software, orchestrating global commerce. You assume it leverages every modern computing breakthrough, but instead, the researchers uncovered blind spots that just border on archaic.
Let's run through these blind spots, because as someone who loves tech, this blew my mind.
Do it.
First up, multi-core design. We have had multi-core processors in our computers for well over a decade. I mean, a standard smartphone has an 8-core processor to handle parallel tasks.
Yep.
Yet, according to the research, none of the runtime systems evaluated are engineered to take full advantage of multi-core hardware through parallel programming.
None of them.
They are treating a multi-lane superhighway like a single-lane dirt road.
The amount of processing power being left on the table there is staggering. And that inefficiency compounds when you look at how they handle thread pool creation. None of these platforms possess the intelligence to dynamically create thread pools on the fly based on historical execution data.
Wait, meaning they can't even look at their own past traffic patterns?
Nope.
Wow. Because a smart system would say, hey, every Friday at 5 p.m., everyone uploads their weekly reports. We usually get a massive spike right now. Let's automatically spin up more resources. But they can't do that.
They absolutely cannot. Instead, human developers have to statically set these limits at design time, weeks or months before the system even turns on.
That is why.
This raises an important question, right? To borrow your superhighway analogy, it's like a city planner paving a road and legally mandating that exactly 2 lanes will be open at all times forever.
Oh, man.
It doesn't matter if it's 3 a.m. and the road is totally empty, or if it's rush hour and traffic is backed up for miles. The system is entirely rigid.
Which brings us to the second dimension, fairness execution. Because if the first dimension was rigid, this dimension is practically blind. We talked about starvation earlier, the nightmare where a crucial task waits forever because other threads are blocking it. None of these 9 platforms possess the intelligence to even detect if a task is starving. They literally don't know what's happening until a human complains.
And part of the reason they can't detect starvation is because none of them calculate task complexity.
Right.
When a message arrives, the system has absolutely no idea if the job it's about to assign to a thread will take a millisecond to process or 5 minutes. It is completely blind to the weight of the incoming work.
So if a platform doesn't know how heavy a task is and it can't detect if a task is starving, how on earth does it decide what to process next?
It's pretty basic.
I saw in the report that almost all of them fall back on the most simplistic scheduling model possible. FIFO, first in, first out.
Yeah, FIFO. It's the equivalent of a grocery store with one checkout lane.
Oh, I hate that.
Right. It doesn't matter if the person at the front of the line has two carts overflowing with groceries and the person behind them just has a single pack of gum. The person with the gum just has to wait. The system blindly processes whatever arrived a millisecond earlier.
Now, I do want to point out one specific exception I noticed in the research. WSO2 was the only platform that moved beyond basic FIFO by offering priority queuing.
Yes, that's true.
They allow developers to flag certain types of messages to skip the line. But even then, that requires human intervention to set those priorities in advance. The system itself isn't dynamically figuring out the best flow.
And that is the underlying tragedy of the current state of EAI platforms. I mean, we are running the modern dynamic cloud on software that acts like a rigid traffic light on a static timer.
A times light, yeah.
A timed traffic light doesn't care if there are 50 cars waiting at the red light and 0 cars at the green light. It just blindly follows its pre-programmed countdown. To stop wasting massive amounts of money in the cloud, we need smart traffic sensors that adapt to real-time road conditions.
So how do we actually build those smart sensors? Because what I love about this research paper is that the authors didn't just, point out the flaws and walk away. They laid out a roadmap for the future.
They absolutely did.
They proposed solutions that require borrowing brainpower and architecture from entirely different fields of computer science.
Yeah, for the message processing dimension, the authors suggest the industry needs to look really closely at GPUs, graphics processing units.
Like in gaming computers.
Exactly. GPUs are the absolute masters of parallel processing. Unlike a standard CPU that might have, a dozen powerful cores, a GPU has thousands of smaller cores designed to process thousands of concurrent threads simultaneously to render complex graphics.
Oh, wow.
If integration platforms could adopt that kind of multi-core, highly parallel architecture, their raw throughput would just skyrocket.
And the researchers also suggested implementing mathematical models to fix the static thread pool problem, right? Like using things like exponential moving averages to predict and adjust resources dynamically.
Yes, exactly. Instead of a human developer guessing the traffic limit 3 months in advance, the algorithm constantly averages the pass load to predict what the traffic will look like 5 minutes from now, and then it smoothly adjusts the lanes automatically.
Okay, but the solutions proposed for the fairness execution dimension are even more fascinating to me because they require a complete paradigm shift. To solve the starvation and FIFO problems, the researchers point toward meta-heuristics.
Meta-heuristics, yeah.
They suggest adopting algorithms based on swarm intelligence and other biologically inspired techniques to schedule tasks adaptively.
This is where it gets really cool.
Yeah, but this is where you have to break it down for me. Upgrading a rigid factory manager with math? That makes sense. But how does swarm intelligence, which honestly sounds like a hive of bees or an ant colony, actually translate to computer threads and enterprise servers?
So think about how an ant colony forages for food.
Okay.
When an ant finds a food source, it leaves a chemical trail of pheromones on its way back to the nest.
Right.
Other ants wander, but when they hit that pheromone trail, they follow it. As more ants use the fastest, most efficient path, the pheromone trail gets stronger, signaling to the entire colony exactly where to direct their energy.
So they are dynamically mapping the best route without a central manager telling them what to do.
Exactly. Now, apply that to a cloud integration platform. Instead of a rigid FIFO queue, meta-heuristics allow the system to leave digital markers, basically virtual pheromones, on processing routes or server nodes that are currently returning results the fastest.
Oh, that's brilliant.
As tasks are completed quickly, the algorithm dynamically reroutes the incoming threads to the paths of least resistance and naturally avoids the bottlenecks.
The system naturally adapts based on the size and complexity of the jobs, keeping the whole digital colony moving efficiently. You abandon simple first-in, first-out rules and embrace a system that constantly evaluates the whole board, the weight of the tasks, the available resources, the priority of the outcome, completely eliminating the digital traffic jams.
And it does all of this autonomously, in real time, without a human developer having to manually tweak a configuration file at 2 in the morning.
So what does this all mean for you as the listener? Why does a deep dive into thread pools, EAI platforms, and swarm intelligence actually matter outside of an academic journal?
It really impacts everyone.
Every single time you open an app on your phone and it instantly syncs your bank account to a budgeting tool, or your company's HR software automatically provisions a new email address, an integration platform is doing the heavy lifting. The efficiency of that invisible digital assembly line directly dictates the financial cost and the environmental cost of running the modern cloud.
I think the environmental cost is a profound final thought to mull over. We've established that the critical runtime systems powering global commerce today are astonishingly still ignoring multi-core processors. They're still relying on basic rigid queues. When you consider the sheer scale of global server farms, massive data centers consuming the power of small cities, how much raw electricity and immense computing power is the world currently wasting just sitting in these invisible digital traffic jams?
It is a staggering thing to consider. Every wasted millisecond of processing time is a literal watt of electricity burned for absolutely no reason.
But the flip side of that equation is incredibly exciting. What happens to the capability, the financial costs, and the energy footprint of the cloud when we finally fix those blind spots? What happens when we let the mathematical brilliance of swarm intelligence rewrite the rules of enterprise software?
It really makes you realize that while we might not be able to point to a jagged white line on an X-ray to diagnose our software bottlenecks, the cure might be hiding right there in the mathematics of nature. Thanks for taking this deep dive with us.